right, so we're looking at solutions to differential equations. So remember, a differential equation has a function. Okay, so this is a function of my variable, so such as a population of a function of time. If I knew the actual function for this, this would give me my solution. This isn't always easy to find. There are ways you can look at the table that we did before to approximate values, and sometimes it's actually possible by looking at these values and maybe even graphing, as you're going to see with slope fields, to see what the equation might look like. So in this section, we're going to tell you what the solution is. All right, so looking at this differential equation, you're probably like, I can kind of see something going on right there, so my growth rate, but this is the actual solution. Okay, this is the solution to this differential equation. So what you're going to be asked to do is, do you believe it? Check it. How you check to see if this is a solution is on the left, and that's what this says, substitute the left and right side of the equal sign. On the left side here, I'm going to substitute whatever my dp of dt is, and then I would take that derivative of p with respect to t to see if the two sides match. So the left-hand side, if I want to substitute, I'm going to take the derivative of this, but I'm only looking at the left, so dp dt. So this says find the derivative of this actual function. That's what this means for the left-hand side. I can find the derivative. The derivative of 50 is just a constant and goes away. The derivative of e, this is that e to the kt, is k e to the kt. So this would be the actual derivative. So now what I'm going to do is I'm going to look at the right-hand side, and I'm going to actually plug in what p equals. So that's what I do here. P equals this, and I get this value, and as I can see, that's the same as the left side. All right, so when you're given a solution to a differential equation and you're asked, is this a solution to this differential equation, you want to take your differential equation and split it up into two pieces. The left side, which is what we did first, we found the derivative, so the change in p over change in t, we found the derivative of this function. And then the right side, remembering that this is my function, I plug it in, and if the two sides are not equal, then if the right side and the left side are not equal, then that is not a solution to this differential equation. Same thing works with c. If we had some initial information, we could solve for it. So with any choice of c will work. But if we're given something like, let's say, select a single solution instead of the general solution, we're given at t equals 0, p equals 60. So I can substitute my p as 60 when t equals 0. And I can solve this and find c equals 10, because e to the 0, that's going to be 1. So 60 minus 50, 10 equals c. And I plug in my value of c. So this is actually, if I have an initial amount, I can plug in for my single solution to my differential equation. So this is only the solution when my initial value is 60. All right, the last part is back to Euler's method. It says find in the missing values into this table, given that I have a differential equation. So dy dt equals 50% of whatever this value is. Assume the rate of growth is given by this, approximately constant. So in other words, we're not going to change, okay, my growth rate over time. I'm going to say at the beginning, that's my growth rate. So we know at t equals 0, y equals 12. So I could put that one in. Then I update this. So I plug in 12 where I see y. That tells me my rate from 0 to 1 is going to be now a rate of 6. So 12 plus 6, I get 18. I could go to my next one. I can plug in what y equals 18. I'm taking half of 18. I get 9. 9 plus 18, 27. And I continue to do this until I can fill up my table. So as you're going to see, if you cannot figure out a solution to the differential equation, you can plug in and do this update based on my value of my function.